Now, Gibbs free energy also has an equation that you should have examined in general chemistry too. And it's an equation that incorporates both the enthalpy, or the heat of the reaction, that's delta H, and the entropy, which is a degree of disorder. Once again, we are not going to do math. All I want from you is to have a understanding of this equation. So delta H gives the relative strengths of bond broken and formed in the reaction. All you have to remember for delta H is that if it's a negative, this favors the products. And if it's positive delta H, it favors the reactants. Once again, we are talking about the difference. Remember, it's products minus reactants. Now, delta S is an interesting case here. It's the degree of disorder. It's the freedom, it's the change in the freedom of motion and reaction. So when those molecules you put together in the reaction vessel, when they react, remember, in a solution, they're moving. They're always moving. They're always in motion. And this motion is important. If you have less motion, you have less likelihood of forming a reaction. Otherwise, how are they going to get near each other, these molecules? So delta S, which is the entropy, is the freedom of motion of the products minus the freedom of motion of the reactants. So now delta S, if it's positive, it means the products are more disordered than the reactants. If delta S is negative, it means the products are less disordered, more ordered than the reactants. And what we need is an increase, reaction resulting in an increase in entropy are favored. Okay, once again, reactions are not going to react or take place unless there is enough motion so those molecules can collide with each other. If you have less motion, they're not going to move. Okay, so you ask someone to run, but you tie their feet, legs, they can't run. They need motion to get somewhere. That's the idea that I want you to keep in mind. What we need, to summarize things, is that we need negative delta H's and positive delta S to contribute to making a negative delta G. And if T delta S, that's the temperature, is small, then delta H is usually equal to delta G. So you can approximate delta G by calculating delta H. Generally, you will see it in your book or in the class that instead of delta G, saying, let's say negative, let's say 1.8 kcal per mole or whatever, like you saw here, it might be written in as this, delta H, negative 1.8 kcal per mole. Now, I want to just do two things before we move on to kinetics, is that on those energy diagrams that we will examine after we talk about kinetics, you might have seen them before. Right here. So if we have, this is A, this is our reactant, and this is B, our product. This is A, and this is B. The difference between A and B is delta G, or like we said, sometimes written as delta H, And this should be a negative value because B is lower than A. So this should be a negative. And we have a name for this reaction. This is called exothermic. Again, you must have seen this before. Releases heat. The opposite is true. So this difference right here is delta G, or sometimes again written as delta H. And this is positive because B is higher than A. And there's a name for this. This is called endothermic. An endothermic. So keep that in mind as we go and think about this, digest it, because the next topic is really the important, is as important as this topic, which is kinetics.